All right. Hi, everybody. Small class today. Now I wish we had a small classroom. We used to have a very tiny A&P section at one time. It was nice and cozy. um, anyway, I guess we'll do it like this in here since this is where we are. So these are just some of our exam stats. So the median was a 76. So kind of a tough exam for some people, but remember we have a retake available at the end of the term, so you can choose an exam to retake during finals week. Could be this one if you want. In terms of other resources, unlike in the fall, we do have an A&P2 tutor available in the tutoring center. So if you want to meet with her, Danny's great. I'm also always available to help during office hours or whenever else you can snag me. So we can talk about that stuff. In terms of assignments coming up, so for Wednesday during the bio advisement day, you should have watched that video on urinary anatomy so that we got the basics down of the kidney and the nephron, so we can start to talk about details of that as we break into the renal system when we get back. So to make sure people actually did take a look at it, there's an assignment to go along with it. So questions that go along with that will be due tonight at 9 p.m. to make sure that you get it out of the way and can start your break free and clear. Our typical weekly quiz, quote unquote, is just 3 questions, just the stuff we're going over for today. That's due Monday when we get back from break, because that's how we put it on our syllabus. But I recommend you just knock it out right after class now. And then again, you can just be free and clear and not worry about this till we get back. Questions about any of that stuff? If you think of any, I'll be here. All right. So what we're going to knock out today is the transport of gases packet. So that was a pretty short one, but the topic can be kind of tricky to get your mind around sometimes, which is why I wanted to save it for when we have some time and when we can really digest that. Okay. So we're going to be thinking about how we actually move gases around in our blood, right? We know that our tissues need oxygen. They need to get rid of carbon dioxide. We've talked about how that's working at the level of the lungs and the alveoli. We've thought a little bit about how that happens at the tissue level, but now we're going to dive in on what's going on in terms of the hemoglobin in the erythrocytes and different factors that kind of affect how easily we're able to actually use especially the oxygen that we have in our blood. I'm not gonna lie, oxygen is really the most important part here. Okay, so just a reminder, when we ended last time, we had mentioned that we have a flow of oxygen and carbon dioxide called our oxygen cascade. All right, so we were thinking I got lungs. Okay. And we're going to draw some tissue here at the bottom. Okay. We're thinking about the flow. I'll draw a heart too. Okay. The flow of blood to the heart and away from the heart, involving the lungs here as well. Okay. So from the right side of the heart, we were heading to the lungs. We make a pit stop there, pick up some oxygen, go through the left side of the heart, and then out to the tissue. Okay. And so as we're going from the lungs back to the heart, out to the tissue, we were tracing our oxygen and giving it a number by measuring it with its partial pressure. Okay. So once we've picked up oxygen in the lungs, we had a partial pressure of 100 for our oxygen. Okay. Then our respiring tissues, our tissue that's making ATP, uses the oxygen. So we see a drop as we return to the heart in that partial pressure of oxygen. Doesn't drop to 0, but we are using up a fair amount of the oxygen, so we drop to 40. Okay, so our partial pressure of oxygen on the return trip is 40. And that's actually happening all the way until we get back to the lungs. When we pick up more oxygen, do it all over again. Our corresponding thing with the carbon dioxide, right? As we start out with blood that doesn't have all that much carbon dioxide in it relatively, which happens to be a partial pressure of 40. We pick up carbon dioxide at the tissue, and that partial pressure goes to 46. So this is the context for what we're going to be thinking about as we talk about transport of our gases and the transport of oxygen, especially on the hemoglobin. We're going to be thinking a lot about how these partial pressures have implications for what's going on with like hemoglobin and oxygen binding to each other. So that's our context. Okay. So oxygen overall is mainly going to be transported by hemoglobin. There is some dissolved in your plasma, just kind of like free floating there, but most of it is attached to one of those heme groups containing iron in our hemoglobin molecule, which has 4 subunits in it. And we'll take a look at that in a second. So about 1.5% of the oxygen that you have there is dissolved in the plasma. The rest, so like 98.5%, is going to be bound onto a hemoglobin molecule. So that's going to mean that for most of our oxygen, when we go to the lungs, we're taking oxygen from the air. It's going into the plasma, but then we're going to bind it onto one of the binding sites in a hemoglobin molecule. We're going to call that loading the oxygen onto hemoglobin. And that oxygen swimming around on the hemoglobin is going to get to the tissue. And at the tissue, we're going to have to unload the oxygen from the hemoglobin. So hemoglobin is like a car, basically, for our oxygen. We're loading at the lungs, we're unloading at the tissue. Okay. So hemoglobin and oxygen are bound together. Yeah, they're bound together. So we're going to have a form of hemoglobin that has an oxygen molecule attached, and we'll often see 1 to 4, 0 to 4 oxygens. Okay, so when we have oxygen on it, we call it oxyhemoglobin, right? Oxy for the oxygen, hemoglobin for the hemoglobin. When we have a hemoglobin molecule separate from our oxygen, that's our deoxyhemoglobin. So deoxyhemoglobin, it's the hemoglobin with no oxygen on it. So hopefully that's pretty straightforward as our terminology to begin with. Okay. Great. So looking at that molecule, we're going to think about hemoglobin as a molecule that can be saturated or unsaturated. So we're often going to draw hemoglobin just as kind of like a box, right? Because drawing this squishy looking thing is unnecessary. But what we're doing when we do that, right, is we're demonstrating that we have 4 subunits, right? So this purple part, the squiggly part, that's our polypeptide chain that has folded up, giving us our primary, secondary, tertiary structure, the shape of that protein. And then we have our quaternary structure where we have the 4 subunits, which would be the little cells in this box, attracted to each other, bound together to give us a whole hemoglobin molecule. Okay, so that's the globin part. The heme groups are in the center, right, of each of those individual subunits. Those are the parts where we have the iron. We tracked the acquisition and use of that iron when we were talking about our erythrocytes, our red blood cells before. Okay, so most of our hemoglobin is in the erythrocytes, so in the red blood cells. So on each of those little 4 subunits, we can, but don't have to, put in oxygen, right? So we have 4 spots for oxygen, right? And we'll see some of them occupied and others unoccupied at different points in time. Okay. So because we can bind up to 4 oxygen molecules, if we've got 4 on there, that hemoglobin is fully saturated, right? It's soaked up all the oxygen that it can. If we were to have 0 on there, right, it would be unsaturated. Most of the time, we're going to see kind of like partial saturation. We're usually not going to see hemoglobin molecules that are all fully saturated. Okay? But that'll depend on where we are in the body. When we are thinking about this, we will note that binding of oxygen and hemoglobin to each other does follow our law of mass action, which is to say that, right, like, so we have our hemoglobin and we have our oxygen separate, right? So our deoxyhemoglobin and our oxygen from the last slide. And then we have that reversible reaction that gives us our oxyhemoglobin. Okay. So what we're saying here, right, is basically just, we say mass action, we're saying that whichever side there's more on, that's what's driving the reaction, right? So we're saying if there's more oxygen, this reaction proceeds to the right, and that oxygen goes on to the hemoglobin, right? If there were less hemoglobin or less deoxyhemoglobin, I should say, or less oxygen, right, we might go to the left, right? So if we are at the lungs usually, right, that's when we're going to think about like a lot of oxygen that's not on a hemoglobin molecule yet. So that's when we'll see this equation proceeding to the right like this. But when we're at tissue, right, delivering arterial blood, lots of oxyhemoglobin. If we have lots of these molecules, these oxyhemoglobin molecules, that's going to push the reaction a little more towards the other side, which is where we're going to free up the hemoglobin and the oxygen from each other. Okay, so we just want to remember that this can go 2 ways, which is how we're going to get that loading and unloading. Okay. Questions so far? Small enough group that. Okay, so hemoglobin with 4 oxygens, fully saturated. Okay. So when we're thinking about oxygen being transported, we could calculate out carrying capacities of blood that are going to depend on how much hemoglobin you have. If you were to fill up every hemoglobin molecule under normal conditions, 1 hemoglobin molecule is going to, 1 gram of hemoglobin molecules is going to carry about 1 liter and a third or so, a milliliter and a third of oxygen. Okay. So per liter of blood, you end up with about 200 milliliters of O2, because the typical person typically has like 2 to 17 grams of hemoglobin per deciliter. Okay. So you could calculate that all out, and you may do that as a practitioner, possibly, depending on what you're talking about. Now, what's happening here in the arteries and veins, though, is not usually full saturation of all of our hemoglobin molecules. Okay, so our arteries get kind of close, right? Our arteries are going to get to about 98.5 saturation. Okay, and that's going to be specific to a specific partial pressure. But we know that the partial pressure of oxygen in our arteries is usually 100. Right? So these 2 ideas are going to be linked together. So that 98.5% saturation is going to look like a bunch of hemoglobin molecules that are fully saturated, but still some number of them that have 1 more spot left for the oxygen. So that's the blood in the arteries delivering oxygen to tissue. When we come back from tissue, we're not going to take all the oxygen off the hemoglobin. Okay? In fact, we're going to leave a lot left so that if you suddenly up your oxygen needs, right, you start going on a run, you start doing something more active, one of your organs suddenly needs lots of energy for some reason, you've still got extra in there. So this is helpful that we don't immediately, under all normal conditions, use up all our oxygen. So in that venous blood, usually we still have like 3 out of 4 of those spaces occupied, and we're just peeling off that final oxygen from our hemoglobin here. So venous blood is actually about 75% saturated still. So we're leaving lots of oxygen still in the blood. Okay. Now this is the trickier part. Okay. So we have a relationship between partial pressure of oxygen and that oxygen saturation. So the percent saturation. Okay. So the curve is going to look like this. Okay. So what we're saying here is if the partial pressure of oxygen in your blood were at 0, that partial pressure is measured in the plasma, but the plasma comes to equilibrium with the hemoglobin. But if you were at 0 in the plasma, right, you would have no saturation of the hemoglobin with oxygen. That makes sense, right? As you start to increase oxygen levels, right, at first, it's actually kind of hard to get oxygen onto the hemoglobin, okay? So that's because putting that first oxygen on an empty hemoglobin molecule is much more difficult than filling up that second spot or that third spot. So the relationship between hemoglobin and oxygen shows what we call positive cooperativity. And that's why we see this sigmoidal kind of S shape here, right? So what's happened here is that as soon as we get one oxygen in one spot on those hemoglobin molecules, it suddenly becomes easier to load more oxygen onto them. So we see this kind of shooting up. So that's why we have this kind of shape at the beginning. Now, all of this is happening at levels that are lower than you would typically see in your body, okay? So what we've marked up here at the top is the situation that we typically see in our veins and in our arteries. Okay, so if we were to read this graph, right, which we could do, so our typical partial pressure of oxygen in the veins is 40. That's what we'll hit first because we're going up. All right, so at a partial pressure of 40, we're going to see that 75% saturation over here on the y-axis, right? So this is showing us that same piece of information just in picture form, basically. As we're trying to fully saturate our hemoglobin, right, we'd be slowing down this loading a little bit because we have to find a hemoglobin that still has space on it, right? And some of those hemoglobin molecules are saturated. By the time we get to a partial pressure of 100, which is what we see in the arteries, we are almost, but not fully saturated. So this is that 98.5%, right? So we're not all the way at 100, but we're getting close. Okay, so we've still got a little room. We still have some hemoglobin molecules that have space for an extra oxygen, but not too many of them. What we're going to see as we go through our next couple of things is we're going to be talking about what can move this curve to the right and to the left. We're going to be talking about rightward and leftward shifts. And we're going to be talking about the affinity of hemoglobin for oxygen. So some of the things that we're going to want to pay attention to as we do that, a particular thing that we're going to want to pay attention to, I should say, is this difference between how much oxygen we have in the veins and how much we have in the arteries, right? So what we're going to see if we move the curve to the right, let's do that to the right first, because spoiler alert, we're mostly going to be talking about rightward shifts. The leftward shifts are going to be relatively rare. Okay. So when we say a rightward shift, all we're going to be talking about is like drawing this same curve a little bit to the right. Okay, so we've just moved it to the right. Right. And this has to do with the properties of the hemoglobin itself. So this would not change anything about the partial pressures of oxygen in the blood. So when we look at this, we would still have a partial pressure of oxygen in the veins of 40, right? So we can see where this curve is hitting that 40 mark for our partial pressure of oxygen. We're still going to have a partial pressure of oxygen in the arteries of 100. So we can see that here. So what we would notice and key in on here, right, is that under a normal situation, what we've done between the veins and the arteries, or reading it backwards, between the arteries and the veins, right, we brought oxygen to the tissue in the arteries, dropped it off in the veins. So the difference in saturation here is really just a description of how much oxygen you lost to the tissue, right? So this is giving you how much oxygen was unloaded, right? So how much oxygen got out of the car when you pass by the tissue. When you have a rightward shift, nothing about the partial pressures changes, and we still have arterial blood going to the tissue, then heading back into the veins, right? So we would still have to account for the difference between our veins and our arteries and that saturation. Okay. But now you can see you have a huge amount of oxygen, right, that you're losing with this rightward shift, right? So you have sent a lot of oxygen into the tissue here when you have this rightward shift, okay? So when we see shifts to the right, we're going to think about these as affecting how much unloading we have at tissue. And specifically, a rightward shift is going to mean we have more unloading. So we're going to see that we have more oxygen being delivered to tissue if we have a rightward shift. And the opposite is going to be true for a leftward shift. So if we drew this to the left, start at negative, although we wouldn't have a negative number, right? But imagine we're going to the left. So just the same curve here. Right, so now if we trace that same relationship between arteries and veins, right, we've actually only removed a tiny little bit of oxygen at the tissue here, right? So a leftward shift is going to mean it's harder to unload oxygen at the tissue, which means the effect is going to be like you get less oxygen going into the tissue and feeding that tissue under these leftward shift situations. So before we take a look at what can cause these rightward or leftward shifts, questions about how we're reading this graph, because I think this is one of the things that kind of twists people's minds up at first. We'll keep going, but spend some time with this when you're studying. Okay, so we're paying attention particularly to how much oxygen is going to the tissues, and that's going to be measured by any differences between our veins and our arteries. Okay. Cool. All right, so we have different factors that have effects on that dissociation curve. Okay. So the first one we're going to mention here is the Bohr effect. Okay. So the Bohr effect is an effect of pH on the affinity of hemoglobin for oxygen. Okay. So what happens here, pH is basically telling us like how much free hydrogen ions there are in the blood, right? That's what it's measuring, essentially. That's what pH is. Okay. So what happens if you have a lower pH, so like something more acidic, is that you are going to have more oxygen getting unloaded at the tissue, which means this is going to be associated with a rightward shift in that curve. And the reason that we can do that, not on this slide, but we'll talk about it here too. Okay, so what's happening to shift that curve, right? The sort of like molecular reason for this, right, is that hemoglobin has a certain amount of affinity for oxygen. And you can think of it as like hemoglobin almost being like a certain amount of sticky, right? So hemoglobin with higher affinity for oxygen, stickier, holds it tighter, right? So if you have hemoglobin holding on tighter to oxygen, it's hard to get it off, right? So that would be a high affinity situation. And that's like what we were seeing, like a leftward shift. Is it's really hard to unload oxygen if we have a high affinity for oxygen. But if we have a lower affinity for oxygen, right, think about that hemoglobin being like a little less sticky, which means that your tissue is going to be more easily able to pull off oxygen, right? So a lower affinity is going to be associated with better unloading of the tissue. And yeah, mainly that. Low affinity is going to be higher amounts of unloading. So for the Bohr effect, what we're saying is that a lower pH, right, so a more acidic environment, is going to make it easier to unload oxygen because that lower pH lowered hemoglobin's affinity for oxygen. Okay, so it changed the shape of that protein in such a way that it's easier to get the oxygen off and a little harder to get it on as well. So this is helpful, particularly when we're thinking about metabolically active tissue. So if we're making a bunch of ATP, right, we're going to be producing carbon dioxide, but we might also be producing things like lactic acid, right? So we actually see a slight pH decrease in tissue that's metabolically active, that's actively respiring, making lots of ATP. So this decrease in pH at active tissue, so think like a muscle that's working hard, right? It's going to be slightly more acidic. So it's helpful that this lowers the affinity of hemoglobin for oxygen, because this causes that rightward shift, which means that the hemoglobin can let go of the oxygen a little easier. So if your muscle's working hard, it wants lots of oxygen. So this is part of why it can do that, one of the several effects that we're going to look at. There's also a relationship between carbon dioxide and this oxygen hemoglobin dissociation curve. Okay. So carbon dioxide also reacts with hemoglobin. So carbon dioxide and hemoglobin together can form carbaminohemoglobin. Okay. And that carbaminohemoglobin can't grab oxygen as well, right? So carbaminohemoglobin has a lower affinity for oxygen than our normal deoxyhemoglobin did, okay? So this means that it's going to be harder to, it's going to be harder to load oxygen onto carbaminohemoglobin, and it's going to be easier to take that oxygen off, right? Okay, so lower affinity. Affinity is always going to mean greater unloading. These two things are directly linked together. So when we have a lot of carbon dioxide, hemoglobin doesn't like to hold on to the oxygen quite as much. Okay. And this is also something that we might see when we have an increase in metabolic activity in, for example, a muscle that's working hard. Right. So we've got that byproduct carbon dioxide being created. Right. That's where the carbon from the glucose is going. It's becoming carbon dioxide. Right. So the presence of that extra carbon dioxide causes this carbamino effect, helping us unload more oxygen in that tissue as well. So this is working kind of like in parallel with the Bohr effect from earlier. Another molecule that affects this curve is something called 2,3-DPG or 2,3-BPG. Super user-friendly name here, but that's what it is. Okay. So this is our 2,3-diphosphoglycerate. It's made in red blood cells when you're in a low oxygen environment. So like if you're anemic, you'd make a little extra 2,3-DPG. If you're at a really high altitude, if you're on a mountaintop, right? Part of the reason it's hard to breathe on a mountaintop is that like there's less oxygen. So at high altitudes, you would also produce more of this molecule, this 2,3-DPG. Okay. Now, making this molecule is inhibited by oxyhemoglobin, which is why you only make a bunch of it at these high altitudes or under anemic conditions. But the purpose of this molecule is to decrease the affinity of hemoglobin for oxygen, right? So when it does that, if we decrease that affinity, lower the affinity of hemoglobin for oxygen, this means it's easier to unload oxygen at the tissue. So this is helpful, right? If you're on a mountaintop, you're in a low oxygen environment, you start to make extra 2,3-DPG, right? This is great because you don't have much oxygen in that air to begin with. So when you breathe in that air, get oxygen on the hemoglobin, right? Even though you have like lower amounts of oxygen because of this low oxygen environment, it's easier to peel off the oxygen from the hemoglobin. So even though you have this low oxygen environment, because of this rightward shift, because of this 2,3-DPG molecule, you're still able to get enough oxygen to the tissue by changing this behavior of the hemoglobin. So you can think about it like if you're going to climb a really high mountain, right? They tell you to get like partially up to a higher altitude and kind of stick around for a little bit to kind of adjust so you don't get too much altitude sickness, right? So part of what you might be doing is kind of waiting for your production of this molecule to kick into gear. So this is helpful under low oxygen conditions, either in space where you are physically, or if you're anemic for other reasons, right? Your body might be kind of under low oxygen conditions, even if your environment isn't. A really dangerous thing, separate from this topic, that also affects your transport of oxygen by hemoglobin is carbon monoxide. Okay, so instead of shifting this curve back and forth, what carbon monoxide does is it directly takes up one of those spots on a heme group. Okay. And unfortunately, hemoglobin likes carbon monoxide better, right? So what we're trying to do usually is get those oxygens on. Okay? But in the presence of carbon monoxide, we have a greater affinity for that molecule. So if you fill up your hemoglobin with a bunch of carbon monoxide molecules, you can't carry any oxygen because the space is full. It's saturated with something else. So you're kind of stuck. This is why people get carbon monoxide poisoning. This is why this can be deadly, is because you can't carry oxygen, even if there's oxygen around, because the hemoglobin likes the carbon monoxide better, has a higher affinity for that molecule. Let's do this practice one, and then we'll mention one more thing. Right, take another minute or so. Let's take a look. Oh, even split between the two. Okay. So what we are looking at here is that final effect, that 2,3-DPG. Okay, so when we have this hemoglobin oxygen dissociation curve, talking about that thing that I drew at the beginning. So if we're going from below sea level to the top of a mountain, right, what we have happening, hopefully, is kicking in your production of that molecule, the 2,3-DPG. Okay, so we're thinking about our partial pressure of oxygen, and we're thinking about our oxygen saturation. Okay, and we know that we have a normal situation that looks something like this, and we're going to mark our partial pressure of 40 for the veins, and we're marking our partial pressure of 100 for the arteries. All right. So a rightward shift, literally just moving this whole thing to the right. Right. And that is one of the effects of high altitude, these low oxygen conditions. Right. So when we shift to the right, we make more 2,3-DPG, which is great because we want to make it super easy to get that oxygen off of our hemoglobin because we don't have as much of it necessarily, right? So we want to be able to use it easily. A leftward shift would do the opposite. So in a leftward shift, right, what we'd be doing is making it really hard to get that oxygen off the hemoglobin, right? So we wouldn't be giving our tissue very much oxygen at all, which is not the situation we want, especially under these conditions where we already don't have enough oxygen. Right. I will mention one more thing. So a way I would recommend kind of practicing these things is we have a number of effects that we're thinking about when we think about these dissociation curves. So I recommend kind of practicing drawing tables of these things. So what you're going to want to be able to do is to name the effect. Okay. You're going to want to know what's actually causing the effect. And we'll just frame it as what would cause a right shift. Okay. So for any of these factors, right, like if a lower pH causes a right shift, then a higher pH causes a left shift. It can go both ways depending on how you influence that factor. So what causes right shift? And then you're going to want to know higher or lower affinity. And you're going to want to know if this is more or less. I'll just do a plus or minus, more or less unloading. So if we were to fill this out, for example, for that Bohr effect, right? So our name of an effect, the one that had to do with the pH, was the Bohr effect. What causes a right shift here is a low pH, aka acidity, low pH, right? When we have this situation, by definition, since we're listing our right shift, right, this means that we're creating a lower affinity. Which means that we're improving our unloading, so more unloading. You want to be able to practice these so that if we describe an effect, describe a change, and think about what that's doing to the hemoglobin oxygen dissociation curve and how well we're able to feed our tissue oxygen, right? We want to be able to do this easily. Now there's one more factor that's in your textbook but isn't written out in the slides. We'll run through it as an example when we get back, but I'll give you guys the cliff notes here, right? Is that temperature also has an effect here. So we actually have four things, basically, four effects that we're thinking of. The one we didn't go through was temperature. So a high temperature causes a right tip shift, which if we're thinking about that super active muscle, right? As it's working hard, it would get hot, right? So high temp would cause lower affinity, would cause more unloading. So I would recommend trying this for yourself as you're studying this topic. Cool. All right, so we'll briefly mention carbon dioxide and then we'll get out of here. So carbon dioxide is also transported in the blood. That's our other gas that we're interested in, right? We're putting carbon dioxide into the blood at the tissue so that we have more carbon dioxide as we're heading back to the heart and the lungs. So for carbon dioxide transport, we need carbonic anhydrase, that enzyme. And this is one of the big ways that we are transporting carbon dioxide in the blood. So this is happening in the systemic and the pulmonary capillaries and in the veins. And we are going to have an effect of oxygen on carbon dioxide transport, just like we had an effect of carbon dioxide on oxygen transport. So there's a back and forth between these two molecules. Here you have an overview of where you have these gases in the blood. So just a note, for our oxygen, we had very little carbon dioxide directly in the plasma. We do have a little bit more carbon dioxide dissolved in the blood, but we're going to see a lot of our carbon dioxide is in the form of bicarbonate. Okay? And as we move into the kidneys, we'll talk about that a fair bit. Okay? So there's more carbon dioxide dissolved directly in the plasma than the oxygen. Most of it's in the form of bicarbonate. Okay? So what we have happen, carbon dioxide plus water with our enzyme carbonic anhydrase gives us our carbonic acid here. That carbonic acid then dissociates into hydrogen ions and bicarbonate ions. And so when we talk about acid-base balance, we'll be coming back to this. So when we have increases in carbon dioxide, we'll see increases in these bicarbonate ions and hydrogen ions. So here we have that effect of carbon dioxide and oxygen on each other from carbon dioxide's perspective. Okay, so we're going to take a vein, just circle here. All right, so a vein is at a PO2 of 40. Okay. Carbon dioxide under our normal conditions here in that vein is at 46. Okay. But we'd have a relationship between our partial pressure of carbon dioxide, any partial pressure, and a partial pressure of oxygen here, related to that total blood CO2. Good. So we'd have more carbon dioxide in blood as we have a greater partial pressure. But the other way we might have greater carbon dioxide in the blood, total blood carbon dioxide, is if we lower the amount of oxygen. So when you have lower oxygen, you actually end up with more carbon dioxide in the blood. When you have higher oxygen, it actually like physically lowers the properties of the blood such that the total amount of carbon dioxide goes down. So we have this trade-off between the two. Okay, so that is it for our transport of gases. These are just describing some of those effects that we were talking about in flowchart form, if you like the flowcharts, but it's not different information. It's just the same stuff in a different form. Okay. So I'll pick up with the kidneys when we get back after break.